Good day, good evening from the Radiant Professionals Alliance. Welcome to HydroniX Talk, the presentation of the Radiant Professionals Alliance. This is Mark Etherton. I am your host. Over some quick rules of the road. Please use headphones with a boom mic if possible if you intend to speak and ask questions. It avoids creating feedback that will destroy people's eardrums. If you have a question that you'd like to ask our guests anytime during the show, please use the Q&A text box, and I will stop our guest from speaking and present him with your questions so that we can answer it in a timely manner. I'd like to thank everybody for attending. I would also ask that if you are not a member of the Radiant Professionals Alliance, that you please join us. You can go to www.radiantpros.org and click on the Join link, and it will take you to the application where you can join this very fine organization. A little bit about the talk show. We do this once a month, bring in guests of different natures and speak to them about their products and services. We typically followed by a Q&A session immediately after the formal presentation, and we have unlimited topics there. So if you've got a problem that you would like our brain trust to address, feel free to bring it along, and we'll enable your microphone and you can throw it on the floor for input from the folks that have attended. These shows are archived for members only for review at a later date. If you want to see it after the fact, you'll have to join the organization. These shows are meant to be fun, educational, entertaining, and fun. If you have someone that you would like to submit as a guest interviewee, send that request to me. It's mark.etherton@radiantpros.org, and I will put them into the queue. Quickly go through some HydroniX news that you can use. The RPA University Spring course offering is currently up and running. You can see that at heatspring.com, and click on the Radiant Professionals Alliance for the Radiant Professional University and see what courses we have available up there right now. And we've got more classes coming. Ray Wolfarth has decided to put together a class on troubleshooting commercial boilers, which should be of interest to people in the commercial business. The IAPMO soliciting technical committee members for the 2018 Uniform Solar Energy and Hydronics Code. Deadline for submissions is July 1st of 2016. And that link right there, if it's going to be hard to write that down. If you want to send me an email, I'll be glad to make a connection to you and Hugo Aguilar at IAPMO, who is in charge of the Uniform Solar Energy Hydronics Code with the Code Development Division for IAPMO. The Uniform Plumbing Code and the Uniform Mechanical Code hearings are slated for Denver, Colorado, which is great. That's my backyard. They're scheduled for May 2nd through May 4th. The first 2 days are typically covered by the Uniform Plumbing Code. The second 2 days will cover the Uniform Mechanical Code. And they've already gotten their agenda put together with all of the changes that have been submitted, which are available at iapmo.org. The monographs for those, both the plumbing and the mechanical code, are available. And if you have any questions in regards to that or you would like to attend, contact Alma Ramos at alma.ramos@iapmo.org. And they do have some hotel discount rooms available for those people that are planning on attending from out of state. Here's our quick lawyer's image disclaimer. The graphics and illustration used in this webinar are presented for educational purposes only. RPA IAPMO does not endorse or recommend the vendor or the product depicted, nor any vendor or product. RPA IAPMO makes no representations, warranties, or guarantees as to and assumes no responsibility for the products depicted, and RPA IAPMO expressly disclaims all liability for damages of any kind arising out of the use or performance of the vendor's products or services depicted. End of the legal statement. There is our guest for today. That's Mr. Robert Barmore. Robert, I'm passing you the ball of power, and you are now live.
Hello, everybody. Thank you very much for your interest in Therma-HEXX and Thermapanel tonight. I'd like to go over all of the potential uses for Thermapanel at this point. And I'd like to start by, first of all, describing what Thermapanel is and how we came to create Thermapanel. As you can see from this first slide, Thermapanel is a high-density polyethylene radiant heating panel that is modular. They are 23.5 inches square. The performing part of it is 3/8 of an inch thick, and then we have a 1 inch thick layer of EPS foam that is attached to the back side of it in different configurations depending on whether or not it's going to be pedestal mounted or ground mounted, and in different densities depending on what the load is going to be on the panel. The panels are hooked up in rows. As you can see from this image, there are 2 inlets at the center of the panel. The fluid comes in on one inlet and then branches off back to the left edge of the panel into that header, where the fluid is distributed evenly down those channels, where it is picked up by the opposite header and back through that exit tube to the next panel in the row. The dots that you see in the individual channels, we call those stanchions. They're weld points in the channels themselves that attach the top sheet to the bottom sheet. Their primary purpose is A, to hold the panel together, and B, to turbulate the fluid as it flows evenly across that panel. So if you can imagine that just a sheet of water or hydronic fluid flowing through that panel from one side to the other, evenly heating or cooling that panel and the surface it's in touch with across the entire surface. We hook these up in rows. We manufacture the rows here at our facility in Portsmouth, New Hampshire. And we designed the project with the owner, the architect, the engineer, whoever is providing the plans for the project and the specification of where the system is to go. We then design and engineer the entire layout and the system. We get very involved with the details. I'll get into that in a little bit. Just to give you a story of how we created this and why we created it, I was an architectural designer and builder in Aspen, Colorado. And we were doing a lot of rooftop patios there where we needed to snow melt them. And we used to pour concrete slabs on top of the roof membranes. And then we would put either, PEX tubing in the slab or underneath the slab up under the roof deck to snow melt those areas. We found that the concrete slabs would deteriorate very quickly, 3 or 4 years, where they were cracking and spalling due to the uneven temperatures throughout the slab when you're snow melting. So, you're hitting a frozen concrete slab that has been absorbing moisture and has frozen, and then you're hitting it with 120 to 140 degree fluid in an uneven pattern, as you do with PEX tubing, and it was causing a lot of stresses in the concrete and causing it to fail. So from that, we decided to start making our rooftop patios with pedestal mounted pavers. And a lot of people, if they work in the residential world, don't know about pedestal mounted pavers. If you work in the commercial roofing world, you would know that. I assume whoever's listening tonight is probably in the HydroniX business. Pedestals are a little screw jack. They're about 7 inches in diameter. And again, we'll show you that here later on in the presentation. And they support each panel on the corner, and they would typically have a 24-inch or 23.5-inch concrete paver sitting on top of our panel or on top of the pedestals. There was no way back when we were doing this about 8 years ago to heat or cool a concrete paver that was up on a pedestal. There was no way of putting PEX tubing in it or near it. There was no way to get cable systems in contact with that surface. And I knew that architects had that, as a major problem with that type of a system, even though the system is a great way to do a rooftop patio. So I also found that with pedestal mounted pavers, the paver in the summer, when the sun hits it, it becomes a giant thermal battery. And because that paver is elevated from the roof, the energy from the sun doesn't go into the building, isn't absorbed anywhere. It just sits in that paver and radiates back into the airspace close to the paver surface where you want to relax and enjoy, lounging on a rooftop patio. On an 80-degree day or 85-degree day, you would typically see 155 degrees radiating off of that patio, which is untenable. So we set about to find a way to have a hydronic system that could sit on top of pedestals and provide a way to get heat in or out of that paver system, and we knew it needed to be modular. After about 4 years of trying different ideas, we settled on a system that was very similar to what you see here. It was originally made out of aluminum, and we found that the aluminum was great, it transferred heat beautifully, but there were limitations to the way it was made, and we decided to find a better way to do it using plastics. We got together with Dow Chemical, and they were just introducing a new type of PERT plastic. Some of you may have heard of it by now. It's becoming popular in the radiant tube arena. PERT is polyethylene of raised temperature. It's designed to compete with PEX tubing, has a lot of the same attributes, except it's not cross-linked like PEX. So that means that you can fusion weld it, and you can also recycle it. PEX tubing is very difficult, if not impossible, to fusion weld, meaning you heat the plastic and you push it against itself, and it would actually bond to itself. We needed something that could do that because we were welding 2 sheets of plastic together and then ultimately welding tubes to it. And we wanted something that didn't rely on mechanical connectors as much as possible. And so this Dow PERT plastic was perfect for us. So we developed this, and we're on our 5th generation panel now. I'll move forward here, get off this slide, make it a little more interesting for you. If there are any questions, feel free to just jump in. Love to answer questions on the fly as we go and get a discussion going, so don't hesitate to do that. Some of the primary uses for our panels, again, are pedestal mounted pavers, but we also developed it so that it can be used in a ground mount scenario. So say if you want to snow melt a driveway, as the picture on the right shows, or if you want to cool a patio and heat a pool with the energy from the sun's energy that's creating that hot patio, such as the picture in the center. This picture is a project in Gateway Canyons, Colorado. It was a resort founded by the Discovery Channel owner, or the guy that founded the Discovery Channel, John Hendricks, has a beautiful museum and a resort there. They had a pool at their hotel that they were paying high prices for propane to heat, but the patio was 185 degrees. This is Southwest Colorado. The patio is 185 degrees, and nobody would use the pool. So they're paying to heat the pool. Nobody would go near it because it would burn your feet if you even thought of touching the concrete. So they built this beautiful 2-pool plus a spa area on another part of the property with a lot of amenities to it, as you can see. But they were going to use solar panels, some kind of thermal solar panels, mounted on beautiful carport roofs that were built like this log roof you see down in the corner of the picture. And the problem was the aesthetics of that wasn't going to work for them. Their engineers had met me at a trade show, and we were just coming out of the gate with the product at that time, and they specified us into the project because we said that we could provide an invisible solar collector to heat pools that would also cool the patio at the same time. What could be better? Value added. A solar collector on a rooftop is going to heat your water just fine, but it's going to be unattractive, and it's not going to do anything else. This patio not only heats the pool and cools the patio so the patios can actually be safe to walk on, it creates a 4th dimension for this place. It creates a comfortable environment, it's safe to walk on, and it creates multiple utility to the area. It can also be snow melted. The pool heaters can be used to snow melt the patio in the winter. We had told them that they were going to save at least 60% of their energy in heating these pools. After 3 years, it's been 100%. They don't know of any time that the boilers have turned on for the pools. As a matter of fact, they said that their largest expense was bringing out a contractor for Denver to find out why the boilers haven't come on. And we're very proud of that fact. So it's been working great. It not only works during the day, but it works at night because the patio holds enough residual heat for our system to absorb that heat to heat the pools during the night. The sun doesn't have to be out for these to work. They also heat the pool in the wintertime. That patio gets to about 70 degrees on a freezing day just from the sun beating on it. and they just want to keep the pools from freezing in the winter, so it works for them all the way around. Picture to the left of the swimming pool is a rooftop patio in Whitefish, Montana. It was a restaurant that wanted a rooftop bar and après-ski setup, and they wanted to be able to snow melt, but they also wanted to provide warmth, radiant warmth to the people on an après-ski afternoon or evening in the winter. So our system went in there, and in the summertime, we put a geothermal system beneath the floor of the building in the basement, and they use geothermal to cool the patio in the summer. So that's another great one with value-added benefits, something that a conventional snowmelt system wouldn't do. On the far left picture, that's just an example of a swath of pavers in front of a glass wall on a resort hotel at Snowbird Ski Area. If any of you have ever been there, it's the Cliff Lodge, and it's above their portico, their new portico. They didn't want to snow melt the entire roof, just about 4 feet in front of the window, so that's what that's for. The driveway on the right is an interesting one. That was our very first project, and it was a lady that needed to be able to access her garage at all times because of a heart condition. She didn't have a lot of money for an expensive snowmelt system, so what we did was we used her boiler. Her household boiler had enough extra capacity where we put a simple zone valve that would provide fluid from the boiler to a heat exchanger that then tied into our snowmelt system here for the driveway. And we melt that driveway beautifully. As you can see, 4-foot drifts here, and we're just using 60-degree fluid to heat that driveway. And it's bone dry, and it's still snowing out in that picture. The 3 different types of applications, and there are many, just think of this as a modular heat exchange system. It can be used in many, many different ways. Again, the first way that we envisioned it was pedestal mounted pavers. As you can see on the left picture, it's our panels supported by adjustable pedestals. And then the pavers, concrete pavers, porcelain pavers, or even natural stone would sit on top of our panels about the same size as our panels. Our panels are 23.5 inches square, so they work with the European model, which is a 600 millimeter paver, or they can work with a 23 7/8 paver, which lays out on a 24-inch grid, which is pretty standard in America. We also have ways of doing it with freeform stone and other odd-shaped stones, where we add a fiber composite grate beneath our panel to provide support 100%. Our panels are not structural. They do not, other than at the edges, they do not support the weight of the stone. They resist the crushing of the stone. Where they sit between our panel and the pedestal, they're very, very strong. They're stronger than the pedestals themselves. They will not crush. But if you stepped on the center of it, you would bend the panel. So they're really just there to be suspended underneath the stone surface and in full contact with the stone surface. That's the pedestal mount version on the left. And that's an example of a curved walkway and how we can do almost any scenario where it's curved, odd shapes and whatnot. We have a lot of different ways of filling the gaps that our panels can't fit in. We'll get into that in a little bit. The next picture in the center is a wood frame deck. And this was a deck where they wanted to use PVC plank decking. And PVC plank decking really isn't terribly strong. It has to be at 16 inches on center. Our panels, again, are 23.5 inches wide. So we designed the framing system to encompass our panels. Our panels sit between the joists, but then we provided a center joist underneath our panel and underneath the insulation to support the center of the panel so that decking wouldn't sag in the center. And it provided a nice structural element for it. That's just an example of the detail we'll go to make sure that our panels work within the project that's being called for it to work in. On the right side picture, that's a ground mount, typical driveway. And you can see where we span the entire driveway. Unlike a PEX tubing system where you would lay it out at 8 or 12 inches on center, perhaps even 6 inches on center, tied to rebar or a mesh, metal mesh scenario. We provide full coverage. And the beauty of this is when you use pavers in particular, the ICPI governing body of Interlocking Paver Institute designates that you shall not have more than 1.5 inches of sand above the compacted ground underneath the pavers for settling purposes. Well, when you put a 3/4 inch PEX tube on top of rebar and then have the corresponding sand that's going to protect that, you're typically going to be at least 2 inches. And you're going to get settling. When that paver gets compressed down by a truck or a heavy vehicle, the paver will hit the PEX tubing, but then it'll rock on top of the PEX tubing and want to settle between those 6 or 8 inch rows. And that's where you get tire tracks that you can see settling into the pavement. That won't happen with our panels. We put a minimum 60 PSI styrofoam full coverage on the bottom of our panels, and then the entire surface of the driveway is covered with our panels. So we typically would say you put 1 inch of sand on top of our panels, and then that gets compacted down to 1/2 inch, and then the pavers are on top of that. The very, very solid scenario. So those are the 3 applications where our system works very well, where PEX tubing really wouldn't work. The pedestal mount, there is really no other way for that to be snow melted or cooled. The frame deck mount, again, unless you were using joist track or something like that, and we have examples on our website comparing joist track with PEX tubing compared to ours. And we're about 2.5 times more efficient at transferring energy than PEX tubing in a joist track. And then, of course, the ground mount providing the support.
Robert, I have a question for you on that framed picture.
Yes.
Could that be used with, like, say, a Trex deck, one of the polyethylene recycled decking materials?
Yes, absolutely. That's, the same as PVC decking. So it's a little bit like a wet noodle. It's not as structural as, say, Ipe wood or mahogany or something like that, or even, some other type of wood like southern yellow pine. So we work with whatever material you're going to use and whatever that material requires for support. We'll design the system for you to work with ours. We'll put the correct type of foam insulation on the backside of our panel to provide the support necessary. Actually, in this framed situation, what we did was the foam insulation on the back of our panels is 1 inch thick. And where we knew that we were going to have those joists in the middle, instead of just relying on the foam to support the panel, we actually cut in little circular holes in the foam, because we cut all the foam with a CNC hot wire. So we were able to cut in little circular holes where we could take the 1/2 inch PERT tubing that we use for our interconnects, and we cut 1 inch lengths of it, and we put them into those little holes on edge, like little mini pedestals. And we put a number of those under each panel within the foam to provide additional stiffness.
Nice.
So that's the length that we'll go to and the detail we pay attention to make sure these systems work. The other thing that we do is, we've got this picture on the left up where you see the triangular hole here at the curb. That's a scenario where we can trim our panels up to half of the panel. And so this third panel in here is trimmed, but it's sealed off. And so we're providing heat across that whole panel. But in this triangular area where it's less than half of a panel, we can't, provide fluid flowing through there. So we would put a filler panel in that's dead, that doesn't have any fluid flowing through it there. And then what we do is we take sheet metal, just aluminum sheet metal, and we put it out over the nearest full heated panel, and it goes out over the trimmed panel. And then you put the pavers on top of that, and it transfers the heat laterally to the paver that doesn't have the heat in it, and it brings the heat in using just the aluminum. So that's how we fill in those little gaps. And I'll show you pictures later that show that, how well that works. So this is an example of the ground-mounted start to finish, where we put our panels in. Down here, we have a little inset picture of a typical irrigation valve box that you would see with a sprinkler system. We utilize those, different sizes of those, and sometimes multiple boxes put together to house the manifold system. This is a Watts stainless steel manifold that's in here. And so that would be positioned in various places around the perimeter of the driveway within the landscaping. And it can be hidden underneath the bark chips, or if it's xeriscaping, under rocks, whatever. It can be hidden so you don't have to see them. And that's how we control the flow through our rows of panels. We're not going 300 feet like a conventional tubing system. We're typically going to go up to 24 panels long in a row. So this driveway would be 12 panels wide. So we were going across and back to a manifold in particular, like this one here that you see. Depending on what the needs are of the customer, if this particular house is a house in Maine that isn't used in the winter, but they wanted the driveway melted. So it wasn't imperative that they melt it super quick. So we did longer runs, and it made it easier to install in certain ways. But if we had a customer that needed a very quick melt, like the one here, oops, this driveway here, this goes from one side of the driveway to the other. Now, these were our original aluminum panels. They had a much higher pressure drop and lower flow rate, so we didn't do long distances back then. But this was just 5 panels wide or 10 feet wide. So we had a linear manifold on each side of the driveway where it was just basically a pipe with a valve every 2 feet that flows the fluid from one side to the other. It works very effectively because we knew we didn't have a boiler system that was going to be able to handle a big Delta T, and we wanted to make sure that it worked well. We also did this into 2 zones with 2 pumps, just in case your boiler couldn't handle both zones at the same time. But in the end, it does. It handles it quite well. So we configure it really. We start from start to finish. We help engineer not only the layout of the system, but the mechanical room, the pump, the manifolds, where the manifolds are going to go, how they're going to sit in the landscape, how do you access them, all of that. We think all of that through start to finish because we think like the contractor. We think if we have to install this thing, how are we going to route the tubing? Where's the tubing going to go? Do we allow enough space for the tubing? Is it going to be buried underneath? Is it going to run along the side? Is the tubing supply and returns? Is that going to supply heat to a certain area as it's getting to the manifold? We think all of those things. And we even help design the mechanical room if necessary.
I presume your specifications for pressure drop and flow rate requirements and stuff are available on your website?
To an extent. We engineer all of that. We don't make the plumber or the project engineer worry about that. We handle all of that. And again, depending on how many panels and what the flow rate needs to be, where the project is located. We have projects that are at 11,000 feet on top of Snowbird ski area, the top of the tram. We have projects that are going into Manhattan at the top of high rises with extreme weather conditions. And then we have other ones that don't have extreme weather conditions where they just need to basically maintain frost in southern states. So we think of all of those things when we engineer it and what the flow rate's going to be and how is the pressure drop going to affect the pump and, how many zones there are, how are the zones configured. There's a lot that goes into it, and we handle all of that. So nobody has to think about that.
What value per square foot BTU-wise do you assume for snow melt? I mean, like as an example with Upinar, who's one of our manufacturer members, they've got a snow ice melt program available that you can plug in the variables of temperature and snow temperature and wind speeds and all that stuff, and it tells you need tubing at this density, and your BTU per square foot per hour will be 125 to 150, whatever it happens to be.
We use those same tables because they're standard tables where they class 1, class 2, or class 3 snow melt systems. So we use those for each area. If it's going to be in New York City, we look at the table, is it class 1, 2, or 3? project, where it's residential, commercial, or a critical situation like a hospital.
Mm-hmm.
And we use those guidelines to provide the BTUs per square foot. Our panels in testing, we've actually, as an example, in testing, we've found that our panels are capable of putting out up to 750 BTUs per square foot per hour.
Yeah.
It's huge.
That's a lot.
Yeah, it is. So, how do we spread that out? If one panel can put that much out, we're delivering X amount of BTUs in a half-inch CTS tube to the row of panels. How far can we take that row out and still, get it to snow melt in a reasonable amount of time and, do the job it's designed to do. So that's where we look at each project and we determine how long do we want to make the rows, what is the pumping pressure that we need it to be, how far away is the pump, what's the pressure drop from where the pump is to where our system is. There's so many different options there that we look at, just like any snow melt system. And the other way you look at this is, we're simply replacing the PEX tubing. Our system is no different than any other snow melt system in the general design and operation of it. We're simply putting a lot more glycol out there. Each panel holds a quart of fluid. So there's a lot of thermal mass there as well that is going to maintain this condition, nice even heating. And same with cooling on the reverse side.
Interesting. This
is a pedestal mount example. This is Hidden Peaks Lodge at the top of Snowbird Ski Area. We put this in last fall. This is a new building. It's funny, when I was a kid, I was about 15 years old. I was skiing at Alta Ski Area, and on the back wall, I could see the cranes building this tower. I have pictures of it still when they were building this back in, oh man, it was like 1969 or 1970. And here we are. I'm 61 years old now, and we were installing our system on the lodge that finally got built up there this past year. That was kind of interesting. So our system is located on the upper decks. There's a deck on this side and then on the opposite side of the building where it's pedestal mounted pavers up there. The slab around the ground area down here is conventional slab with 3/4 inch PEX tubing in it. We didn't handle that. Another contractor did that component of it. And because again, you can't melt a pedestal mounted paver scenario with PEX tubing. We wish they had put our panels under the entire slab, because we think the slab would have performed much better than it will with the tubing. But it was early in the game when they specified us, and they were willing to give us a shot where they knew they needed us, but they wanted to use the tried and true way for the other part. Ultimately, they're going to be replacing the entire plaza at the base of this tram with our system, because it's a rooftop scenario. It doesn't look like a rooftop, but they've been shoveling snow down there since the 1960s by hand, and they're getting ready to start doing it the smart way. So this is these pictures here are the left picture. Again, you can see where the pedestals are set. And what is the process for doing this, and how do we work with the contractors? When we sell one of these projects, we provide in the budget for selling our panels, we provide an allowance for us to send a person out to guide and instruct the installing contractors. And I say contractors plural, because you have not just the mechanical contractor that's responsible for putting our panels in and hooking them up and testing them, filling them, and getting the system running, but we also coordinate the roofer, because the roofer is typically the one that's putting the pedestals and the pavers, setting those components, but it's the mechanical contractor that's setting the panels on the pedestals. So we go and we coordinate everybody, and everybody really kind of enjoys it, because the roofers, I think they get bored just setting pavers all day. So this is an interesting new thing for them. And quite often the roofers pitch in with helping put the panels down. They like working with it. So what happens is the roofer sets the pedestals, levels them, and then while he's doing that, the mechanical contractor opens up the box, unfolds the rows of panels because they come folded up in boxes that are 7 foot long. They unfold. We have a special S tube that connects the panels to each other that allows the panels to fold up like a Z brochure. And then they unfold. Each row is marked with a permanent label on each panel that tells you what section, zone, and row that row goes to, and it corresponds with the plans. And then we take a piece of 1x3 wood strapping, and you lay it along the edge of the pavers. And I think we have pictures of this later on, showing how that works. I'll get into that later. So then that gets placed onto the pedestals, and then the roofers come back and they put their the pavers on top of the panels, while the mechanical contractor hooks up the supply and return tubes to the manifold. And then they prepare the next row and so on and so forth, and you work your way across the roof, and it works out nicely. And if everybody's got their act together and showed up with the proper tools and whatnot, which we try to coordinate with everybody and get everybody educated about, from the mechanical contractor, the GC, and the roofer, we try to get them all on the right page so they know what's expected of them on the day of installation. These are an example of some pretty neat projects that we've been involved in or will be involved in. This project on the left is a new tower that's going in New York City in the Hudson Yards project. It's a high rise. It's called Tower A. It's going to have the highest observation platform in Manhattan. And they were calling for pedestal mounted pavers. And the pavers are 4-inch thick granite slabs that are triangular shaped. And they're about 5 feet on each edge. So they're about 650 pounds apiece. These are going to sit on this cantilevered deck that's on the 67th level of the building. So they needed to snow melt that, because at that level it has to be snow melted. And they also have to make sure that they don't have frozen dew and frost on that surface at all times. So how do you do that? How do you incorporate a modular system that is roughly 2 foot by 2 foot onto a scenario like this, where you have these triangular shaped pavers that don't line up with anything with our thing? Oh, and then by the way, they're going to have a window washing rig that rolls out there on this thing that weighs 14,000 pounds per wheel. So it's got 4 wheels. Each wheel is engineered to have a maximum capacity of 14,000 pounds. It's enormous, 7 tons per wheel. So we are working with the engineers in devising a platform that will support our system. We're able to add 100 PSI insulation to the bottom of our panel, which will support 14,000 pounds. And so we're creating a platform with fiber composite panels, grates that sit on styrofoam pedestals. The styrofoam pedestals will be made out of 100 PSI foam as well. And it's an interesting project of how that works. So instead of the typical adjustable plastic pedestal, styrofoam blocks are glued to the deck and built up to a height that's above where they need to be. And then that contractor uses a rail-mounted hot wire system to cut them all off at the same level. So you've got all these little pedestals of styrofoam that are very solid and can support a lot of weight. They'll then support a fiber composite grate system, and then our panels, and then the pavers will sit on top of ours. And that's the plan. So that's another extreme situation where we're working with the biggest engineers in the world to solve that problem. The picture in the center is a Google office that's located in Pittsburgh. And it's the old Nabisco cookie company or cracker company factory that they built another building across the road from it, and they needed to connect it with a 2-story Skyway that it's an elevated bridge that has a rooftop walkway. And this thing pitched at different angles. I don't know if you can see by looking at it, it wasn't a dead level scenario. And they had a very tight tolerance for how much room they had for us to put our system in. As a matter of fact, we had 5/8 of an inch leeway beneath our insulation to the roof deck. And that's why you can see our supply and return tubes here running underneath, just barely making it to supply and return. Oh yeah, and we had to supply and return this thing from one end. It's a very long Skyway that we had to supply and return from one end. So
Robert,
that
I have
was
a question for you.
an interesting challenge. Yes.
How are the panels connected to the distribution piping? Are you using PERT only, or do they also work with PEX?
You can use PEX. You can use almost anything. We supply for our interconnects between the manifolds and our panels. We supply the same PERT tubing, the same resin that our panels are made with, and we supply that with the system. We can supply fusion weldable connections depending on how it's being used, and really, you know, is pressure drop a big consideration? If pressure drop is, we prefer to use our fusion weldable connectors because we're not providing any inclusion as you would with a compression fitting, or not a compression fitting, but a PEX crimp fitting. But quite often PEX crimp fittings are what people like to use. They're quick and they're fast. And if we know they're being used, we design it in a way where, you know, we take that into consideration in our pressure drops. So it doesn't usually affect it too much because the way this tubing is welded to our panel, it welds over the inlet. So we have that restriction at that point as well. So if there aren't too many rim connectors in the line, you know, one on each end, then it doesn't make any difference. If it's going to be buried under poured concrete or a more permanent situation where it'd be very difficult to get to a problem or corrosion is a concern, then we would supply our fusion weldable fittings, and we can supply the tool that is used to do that. If any of your contractors have ever worked with PPR tubing or Aquatherm, it's the same tool that's used for that, just with much smaller die sets to fusion weld it.
I had another question pop up too that wanted to know if you've tested the oxygen permeability of the PERT tubing after it's been fused, and we haven't gotten to that point yet, but I was going to respond to him that this is a non-barrier system.
We'll talk about oxygen. Our system is a non-oxygen bearing system, and it's never going to be oxygen bearing. It would be way too cost prohibitive to introduce an oxygen bearing layer into our panels. So there would be no point in using oxygen bearing tubing for the interconnects or any of the components in this. So we always specify that you use stainless steel heat exchangers, stainless steel pumps, or bronze pumps. We always specify a good spiral vent type vent behind the pump for oxygen elimination, and that's the way the system is designed to work. It's just if you've got an iron boiler or a steel boiler, then we would say you've got to put a heat exchanger in the loop between the two.
I really think cast iron and ferrous components in heating systems are becoming a thing of the past anyway.
I do too. We have had zero resistance on that, zero problems with it. Even the expansion tanks, you want to use the bladder line, the expansion tank where the fluid's in the bladder, not on the outside of the bladder. Those are the type of things that we look at and specify all the time. So yeah, it's no problem whatsoever. As a matter of fact, as I'm going to be going to the meeting in Denver next month to introduce new language. They came out with a new rule that said that all HydroniX systems have to be oxygen-bearing components. They didn't know about our system when they came up with that. And then there are other systems where, the cost of oxygen-bearing tubing versus non-oxygen-bearing tubing is quite significant. So if you're using a stainless steel boiler, what's the point of having an oxygen-bearing tube at almost twice the cost? So they're going to change that language. The people from the Plastic Pipe Institute are introducing the language, and we're going to reinforce it as well. So further here, the two pictures to the right, that's the same building. That's 20 Times Square. That's a project that's coming up for us. It's at the head of Times Square in Manhattan. It's going to be the 701 TSQ. That's a rendering of a giant digital sign. It's going to be the world's largest digital sign. And right here where the lady's face is another rendering of it with the hotel behind it. This is a 5-star Marriott hotel. And at the top of this is a rooftop patio. And our system is specified to be in that. And what's unique about it is they're going to have a canvas area over part of this with side curtains so that they can provide a radiantly heated space for people that are enjoying weddings and certain events and certainly New Year's Eve, and have that radiantly heated in the winter. And they wanted that radiant heat to come from the paver surface. And those pavers are going to be about 18 inches off of the deck. So it's all elevated. How do you do that? Well, our system is the only way to do that. So we're going to create a zone that would be under that tented area. Then the part that's not tented will have another zone that will really be there for snow melting. And also in the summer, they want to cool this because it gets very hot. So we're going to have a chiller system that chills it as well. So that's a neat project. So between that and the Tower A project in Hudson Yards, we're in some pretty neat projects right now. This is a close-up, complete job picture of the Beaumont Hospital in Royal Oaks, Michigan, Natural Birthing Center. There was a kind of a leftover roof space between a bunch of hospital buildings that were built around a central building. This is the 3rd story, and this was like a forgotten rooftop. So somebody donated a bunch of money to the hospital for a natural birthing center, and they needed a walkway for the ladies to walk while they're getting ready to give birth and to move things along. So that's why this circular pathway here. And we were called upon to provide the snow melting for all of this. And then back here in the corner is the PVC deck, where it transitions from PVC to concrete pavers. So we did that. And this is an example here on this picture in the center where we utilize sheet metal to take heat from the fully heated panels out over the non-heated panels where the filters are located, and it generates the heat out there. And you can see from the picture where snow is all melted, it all works quite well. You can also see here where the manifold is located beneath the pavers with access. So there's about 4 or 5 manifolds around this thing under certain pavers. So when a contractor has to go and work on the system, air it out or do whatever he has to do, you just look at the plan and you can see what paver that the manifolds are under, and you can go over there, lift the paver up. And we provide extra tubing on our panels over an area like this where you have a manifold. So there's like a big loop of tubing. So you lift the paver up, you lift our panel up, and you don't have to disconnect the panel from the system. It just comes up with the tubing, and then you can make your adjustments, put it all back together, and you're in and out in no time. If you ever do have a leak, or go ahead.
You do think like a contractor.
Because I was one for 30 years.
There you go. And another question popped up too. They wanted to know roughly what kind of cost per square foot the system runs.
Okay, the panels are $17 a square foot, and so that's $68 a panel. And that may sound like a lot, but with the value-added benefits of what these provide, it's actually quite reasonable. And installed costs typically range anywhere from $23 to $30 a foot, and that would not include the boiler. So that would be the labor. Like this project was a union project on a hospital near Detroit. The labor costs were pretty high there, and but it provided a service that they wouldn't have been able to do this otherwise. This simply wouldn't exist if they couldn't put our system in. So that's why we really don't go after projects where, if it's a price-sensitive project, if it's kind of a price-sensitive residential project, that's not an area that we're going to really be going after. unless they need it for pavers or pedestal mounted pavers. If you're heating a swimming pool and you want to cool a patio around a swimming pool, it pays for itself, period. It's a no-brainer on that one. If somebody is snow melting, it's probably a higher end project that they can snow melt. If it's commercial and it's like this, they absolutely have to have it. And it installs very easily as well. It's not a hard thing to install. And like I said, we provide the assistance, and we even provide the assistance on how do you lay out these straight lines going around these odd circles, right? That's what these strings are all here for. We were laying out strings and grids to line this all up, and it all came out pretty much perfect all the way around. They even showed up with the wrong size paver on this project. It took 2 cranes to put the pavers up onto the roof of this project. You had to crane it up to an upper roof and then crane down into here to get the pavers in there. And the architect, everybody had specified 24-inch grid layout, which means 23 7/8-inch pavers. The paver company delivered 23.5-inch pavers. Whoops, and they were all in there. They're all inside the project here. What do you do? So as you can see here, this paver is not lining up with the edge of our panel. What we did was we laid our panels all out with the pedestals as we designed it, because our system was not adjustable at that point. We've since made it so it could be adjustable on the fly if needed, but at the time things were fixed. And so what they did was they went and brought in extra pedestals, and when a paver got too far away from the pedestal, they would throw another pedestal under it, and that's how they solved it. It wound up coming out okay. But again, that's where we work with the contractors and the engineers and the architects to solve problems from start to finish. We don't just ship the panels and forget about it. We work with them start to finish.
I have another question for you. You want to know if you direct pump the pool water through the panels, or is there a heat exchanger?
We recommend a heat exchanger. Pool water is typically not going to be very clean, and even though it's coming through a filter, you could, or because we're using Dow's PERT 2499, it is chlorine-resistant plastic. It's designed for domestic recirculating systems. That's why we chose it, so that it would be a product that had a track record and a product that was highly durable. We want this to last minimum 50 years. Yeah, you could pump pool water directly through it. It would depend on the chlorine levels. If the chlorine levels are outside of a certain parameter, then you just have to know that the system could degrade over time.
Yeah,
but
that would be my biggest
concern. I would say, why wouldn't you just put a heat exchanger in the loop?
Sure. Do you have any dealers in Hawaii?
We don't. We don't work through dealers. We work direct. The way we sell is if a contractor comes to us, we sell directly to that contractor. Typically, we get projects by being specified by the architect, the pool designer, the landscape architect, the engineer. Those are the people that typically specify us. And then when the contractor gets the project, they just see Therma-HEXX Thermapanel is specified, and they call us and we give them the price. And then we work directly with that contractor to sell directly to him. We'll also sell them certain components. We'll include the interconnect tubing and any fittings to connect it, the manifolds. We can include glycol feeders, because that's not something that's commonly available to a lot of people. And we're starting to get OEM relationships with the pump companies, B&G pumps, and other pump companies as well. We like to work with B&G. We like to work with MagnaFlow 3 pumps from Grundfos. They all provide high head, low flow pumps. We'd love to work with Patio pumps. Unfortunately, they don't have a lot of high head pumps, but any of their pumps that would work with the scenario, we look at all of them. We look at what the contractor likes to use. If a contractor tells us, look, we've got all Patio pumps in this house, then we look at Patio and see if we can get a pump that'll fit the application. If not, then we'll move to one of the pumps that, we know works for the situation. So we know what it's like to be the contractor. We like to work with a contractor. If we can get the contractor a better deal on the components, we'd sell him the components, at a good price if it makes sense. And some contractors just want the whole thing as a turnkey system and don't want to have to hassle finding the components, and we'll do that as well to a point.
Patio just merged with a European firm, so you'll probably see some changes in some of the pump availability. They're going to start doing mostly DCCM circulators, and I think they're going to expand their line as well.
Yes, yeah, they are, and it's interesting. The whole hydronics industry is consolidating like that between Patio and Watts. There's a lot of consolidation going on there, and perhaps one day we'll be part of that. So moving on to performance. If you go to our website, these are a couple of snapshots of tests that we have on our website. I highly urge everybody to do that because they're very eye-opening. If you go to our Thermapanel page and click on videos, the first two videos show these comparisons between our system and a conventional tube-based system with pavers, which is what this is. And also we have, in the second video, we show it with various materials from drywall, ceramic and concrete pavers, plywood, and sheet metal, because there's a lot of other applications that our panels will work with, we'll get into later. So in looking at this on the left and right picture, it's probably pretty obvious which one is going to be the Thermapanel. On the left, we heat that paver up very quickly, very evenly. It's interesting how you can see in the thermal imaging here on the right picture, you can actually see where the two inlets are because it's slightly cooler. And I mean slightly cooler because, they don't have as much contact right there. So you can see how even that heat is. It's good for the concrete because it's getting heated evenly and it's not putting stresses in that concrete. It also allows you to melt the snow very quickly. And in reverse, when you're cooling, it allows you to fully, every square inch of that paver is losing its energy evenly from one side to the other into the fluid. So again, we have a quart of fluid in that panel flowing through there at all times, and from anywhere from a quarter gallon a minute to a gallon and a half a minute is the typical flow rate that we see. When we set up this rig, we brought the flow and return in evenly right here at the half. We keyed it in, and so we flow out to ours with a 1/2 inch tube. We flow out to theirs with a reverse return parallel setup. So it's very fair. And on this one, the tubing is set in sand, compacted sand that's insulated beneath, the same as our panel's insulated. And with the paver sitting right on that sand as if it was a driveway paver setup. And you can see the paver on the right never fully heats up, ever. It just doesn't. It has too much edge loss and surface loss to ever catch up to what our panel does. And keep in mind, they're both being fed with a 1/2 inch of fluid, 1/2 inch tube of fluid, off of a 1/2 inch branch. And so they're getting the same flow rate, and we check that. Each side gets the same flow rate as the other side. And we were 2.5 times more efficient at transferring energy than the tubing side.
What supply water temperature was going through the panels at that point?
Well, you can see here the hottest temperature is 116 degrees. I think we were at 125 to 130 degrees going through.
Thank you.
Might have been less, actually. Might have been 120.
I'll have to introduce you to my 4-way reversing valve one of these days.
Oh, I've just created one with Belimo, where we're going to send the fluid from one side. This is a scenario, and we're kind of getting into an area here where we could discuss that. When we have a really long run, of panels. We recently did a little sidewalk for a lady here in our town where we did one loop, and it was 27 panels long. Normally, we don't go more than 24 panels, but somebody measured wrong on the job site, and we had to add extra panels. So the fluid is flowing down one side of the sidewalk and then reversing and coming back the other half of the sidewalk. So the left side of the sidewalk heats faster than the right side of the sidewalk, right? Mm-hmm. And that's fine if you've got, an hour or two to wait for the whole thing to melt. And, like this driveway, the whole thing is melted just beautifully. But if you want that whole thing to melt faster, then what do? Well, you would, send and return from the two ends and split it off and have two loops. So we would cut that 27 in half and send it through two loops. Or what if you reverse the flow from one side to the other on a cycling relay? So you had a valve, a three-way valve or a six-way valve, two three-way valves or one six-way valve that on a timer reversed itself every minute, 2 minutes, 30 minutes, whatever, where you're flowing from one side to the other and then back the other way. So they're really heating from both ends. So that's something we're going to be experimenting with. So I don't know if that ties in with your reversing four-way valve or not.
I used that method about 20 years ago on a driveway that was about 1,000 foot long. And we had one loop that went from the top of the driveway down 300 foot to another manifold. It was more than one loop. There was obviously at 9 inches on center, there was a whole bunch of loops because the driveway was about 10 foot wide.
Yeah.
And we put that section on this four-way reversing valve, and you could hear the ModCon boilers when that valve would reverse. It would start pulling the hot water back from the radiant zone, and the boilers would see it, and they'd slow down, and then all of a sudden the cold water would show up, and they'd start ramping back up again. It was quite the amazing system.
So what was it? Was the end result that it would heat a lot faster? Because my concern is what you were just mentioning. Now you've spent this energy getting the first half heated up, and now you're reversing it, and you're sending cold fluid back through that heated area, and is that going to cool it down, or and what time cycle do you reverse that? How did that work out for you?
It worked great. We actually had the balance of the driveway was done conventional parallel tube circuits with counterflow spiral installation of the tubing itself, and you couldn't discern the difference between the conventional system versus the one that was straight shot from one manifold to the other one that had the reverser on it. And the upper end of the driveway actually seemed to melt a little bit quicker. Looking at it with an infrared camera, there was really no discernible major difference, but that top part seemed to melt faster.
Well, I'm excited to try that myself. I think we're going to make up panels that have that kind of a control system and valve system as a standard selectable component in our systems where we have long runs like that, because we get long, narrow runs. And if we can do that instead of putting manifolds in the middle of the run and just send and return from each end, that would be fantastic.
I'll send you a drawing.
Yeah, please do. So in this left picture, this is part of our first video that you saw in the previous slide. This is the second half of that video where we put a bin on under the two pavers that you saw. Ours is on the left, the tubing side is on the right, and we dumped in an amount of granular frozen snow, and we dyed it blue so that it was obvious to see. After I believe it was either an hour or an hour and a half, might have been an hour in this one, the Thermapanel side pretty much fully melted, and the PEX tubing side is just starting to melt. As a matter of fact, after another hour and a half, there was still a lot of snow left on the PEX tubing side. And our side, of course, is bone dry. So there's just no comparison in the efficiency of our system. This driveway here is in Long Island in the center picture. This was this winter, and it melted beautifully for them, very evenly. This was a back and forth. So this driveway was about 24 feet wide, and we sent and returned in loops back and forth across of this. compare that to a PEX tubing system. Here's a typical PEX loop system with pavers. And so you can see how it's melting from the tubes out. So that creates a lot of runoff. Our system, if the system is dialed in properly and turns on at the right time, it tends to evaporate the snow from the get-go. You don't get a lot of accumulation first on the system because as you see in the left picture, we heat up the paver rather quickly. And so we don't get a lot of accumulation before the snow melts. You can get the system up and running very quickly. And again, that can be up to the homeowner too, because they may want to run it more efficiently where they're running very low temperatures, and then it'll take longer for it to heat up. So it's a numbers game of how do you want it to work? Do you want to hit it with higher temperatures and have a very quick melt, or do you want to use lower temperatures and be satisfied with a slower melt time? But what you don't get is this kind of striping that you would with the normal PEX system, which can create a lot of runoff and other issues while you're waiting for it to happen. But this just shows the efficiency of it. Not sure, if that's as accurate a comparison as possible, but it's what we had there.
Yeah, it's a term we refer to in our industry as acceleration. And reminds me of my brother-in-law when he and I were out fishing in his boat. They had two V8s in it, and he looked at me and said, "Do you want to get there, or do you want to think about it?"
Exactly.
We got there in a hurry.
Yeah, and at what point does the efficiency of the boiler come in to, it's like if you're driving 30 miles an hour down the road or 80 miles down the road, 80 miles an hour down the road, you're going to get there quicker, but you used a lot more fuel going 80 miles an hour than you did going 30.
Right.
So at what point do those two lines cross for snow melting for you? And everybody has to weigh that on their own. This was an early example. This slide is a great example of the thermal cooling properties of Thermapanel. This was a little sidewalk experiment we did where we put Thermapanel underneath these pavers. And at the yellow line, to the right of the yellow line, is Thermapanel. Thermapanel stops at that yellow line, and then for 2 feet to the left, there's no Thermapanel system. It's just pavers, on the ground. So we took two X-Tech thermal thermometers, digital thermometers, and holding them at the same time and taking the picture. You can see the two outer ones where these pavers are 6-inch square, so they're about 18 inches apart, and the one on the Thermapanel side is 113 degrees, and the one on the non-Thermapanel side is 150 degrees. And this was a day that was roughly 80 degrees out here in Portsmouth, New Hampshire. So just 18 inches apart, that's how, there's a huge difference in temperature. And then we brought the two guns right next to each other, shooting very close to the paver, left and right of the demarcation line between them. And there's a 20-degree difference right in the same paver within 2 to 3 inches of each other. Huge difference. That shows how well the Thermapanel system cools that pavement. And all we were doing was running 60-degree tap water through the panels at that time to cool it. So it's dramatic how well it works. So this is the gateway project that I spoke of in the beginning, and you can see the installation of it. These were our original aluminum panels. These panels were originally, because they were aluminum, each one was connected to the next one with a little push-on connector. And so, we got away from that because we didn't want aluminum. We knew it was going to be more fragile than plastic, and we didn't want to have a mechanical connection every 2 feet. We wanted to eliminate that. We wanted to have as many fusion welded connections as possible to eliminate, potential future failure. But this project turned out spectacular. It was 10,000 feet of patio in a very free-form manner around all these gardens, around all of these pools. It's 3 systems with 3 heat exchangers. Each pool has its own And the spa here on the right picture has its own area and heat exchanger. We keep the spa to up to 104 degrees, and we use a designated area of the patio here where we did longer runs of panels to get the heat up higher in temperature than we did in the areas that we're using to heat the pools. And so what we have is just a simple differential controller that has a sensor for each section. We have a sensor that's in the paver and a sensor that's in the pool return pipe before the heat exchanger, and then that goes to the Pentair. I think it's called a Sun Troll or something like that. It's no solar. I can't remember the name of it. It's made by Pentair, and it's just a simple solar controller, differential controller. So it just senses the pool temperature and the paver temperature, and however we set it to turn on. If the pavers are hot enough at their design temp and the pool water's cool enough, it turns on the pump that pumps the glycol through our panels, bringing the heat back to the heat exchangers. The pool water always flows through the heat exchangers, so the heat exchangers are located after the pool filtration system and before the pool heaters. The pool heaters that are now just big cases in the room that don't ever turn on. And so the design was that if there wasn't enough solar energy to heat the pool, after it leaves our system, then the boilers would turn on and make up the difference going back to the system. It was a typical system that you would use with any kind of pool solar heater. In this scenario, the system works so well that the pool heaters never ever come on.
Was that a Pentair Solar Touch?
Yep, that's it. Thank you.
It's courtesy of Kurt Albershard.
Appreciate that. Yeah, great unit, very easy to program, very easy to use, very inexpensive. Great units.
It's probably actually made by one of Watts' subsidiaries.
Techmar.
Yeah.
Probably. Yeah. Yeah, and we work with Techmar. We love Techmar controls. We understand them, so we usually specify them. But if somebody wants to use Honeywell or some of the others, that's fine as well. It doesn't matter to us. It's whatever, again, the contractor and the building owner wants to work with. With these commercial projects, we're getting into a lot of building management systems. So we're specifying the Techmar units that work with BACnet and that sort of thing. This slide just gives you a quick, visual of, throughout the year, the difference in temperature from what you would have with a Thermapanel system in a patio versus a system without Thermapanel. And, back in the Gateway project here, when they called us to do this, they were really just looking for solar heaters for the pool. And we sold them on the fact that we had spoken with their engineer at a water park trade show, and we talked about the fact that Thermapanel was an invisible solar collector. And they never really considered the fact that we would cool the patio. And what sold them on us was the fact that we would cool the patio, because they knew their patios get to 185 degrees, third-degree burn territory. So with this project, when they keep these pools at 86 degrees on the hottest days, which are 105 degrees, we bring the patios down to about 140, 138 degrees. That's still pretty hot, but you're not going to get a third-degree burn from it. And you're probably going to be able to lay under one of these palapas and be comfortable. We asked them, hey, if you want, bring the pools up to 96 degrees on those days, and you'll bring the patio down to 126 degrees. That's a lot more comfortable. We also suggested a geothermal system to dump extra heat, but they didn't want to go through that expenditure, and that they just weren't ready to do that at the time. So they put in waterfalls between the spas. There's one here, there's another waterfall over in this pool as well. And that also provides some cooling from the waterfall.
Boy, howdy.
What's that?
I said, boy, howdy. We have a place here in Denver that is called Cable Land. It was owned by cable magnate Bill Daniels.
Yeah.
And he donated it to the city of Denver, and it's supposed to be the official mayor's residence, although none of the mayors have ever lived there, so they just use it for parties. And they hired us to put a new pool boiler into the swimming pool, and they had a large water feature that was a waterfall. And as long as I kept that waterfall off, we could keep that pool perfectly warm year round. As soon as I turned it on, man, the temperature would drop like a rock.
Wow, interesting. Well, we knew with this design, this was one of our first 7 projects, and we didn't have a lot of data yet, but we, based on from our own internal testing that we had done, we estimated this was going to produce about 1 million BTUs per hour more than the pools could use. And, we said, you could put less of our system under the patio and just designated certain areas of the patio that you really want to cool down and that are, always in the sun to heat these pools. Well, they decided they wanted to cover the entire patio with it. Good for us. It was about $250,000 project. And so we did that, but we knew that they were going to have more energy than they could use. But at the same time, at the shoulder seasons, when you start looking, out here on the shoulder seasons, that extra energy is helping them. And that's why their boilers never come on. So how do we control it in the summer when, they're up in this area here where it's still a little hotter than they would like? How do we control that? Well, we've suggested, now that we're making our panels out of plastic with fusion welded connections, that they use our panels buried in trenches in the ground for a geothermal heat sink. Again, when you put our panels in the ground without insulation on them, they'll put out 500% more energy per square foot than a slinky tube geothermal system will. Remember, we were putting out 750 BTUs per square foot per hour off one side of our panels. So that's 1,500, on both sides if it was in a geothermal scenario.
It's some pretty good heat.
It's huge. So they could dump a lot of heat into the ground, and then they could use that heat because it would become a giant thermal battery in the ground, and they could use that heat later on in the year for heating. Moving on, our radiant system configuration, pretty standard. You've got our system that, like you would have just where your PEX tubing loops would be, or a radiator system would be, coming off of a standard manifold. Depending on whether the boiler is above our system or not, you may want to put check valves in. So if you ever had a leak down here and the boiler was up on another level above the system, you might want to have check valves to prevent all of the glycol from running out the system if somebody had broken a line or something. We also, on our supply manifold now, we send them with a 40 psi pressure relief valve on one of the ports. We provide an extra port on the manifold just for that. The purpose of that is typically when the system gets installed, the mechanical room isn't ready yet to be hooked up. And even if it was, we'd still want to provide a way to protect our system from overpressurization. We've seen it where, hold on, I've got a cough. We've seen it where contractors have closed off the individual loops on the manifold and failed to open them all up. And then you'll see one of the zones overpressurize just from the sun expanding the glycol in the system and potentially blowing up one of the panels. Also, when they do their initial air pressure test with an air compressor, sometimes the contractor shows up and it's set to 120 psi. He hadn't dialed it back to the recommended 30 psi, and kaboom, they blow a panel up. So we now ship it with a 40 psi pressure relief valve so that they can pressurize it without worrying about the relief valve going off, but pressurize it to the recommended 30 psi. And then after the system is up and running, and it also prevents, inadvertently the contractor putting in too big a pump. And the first time he turns on the pump, again, overpressurizing. We've seen that happen where an engineer specified a pump and it was putting out 80 psi of pressure to the first panels in the system and stressing them out. We don't want to see that. And that's why we now specify the pump. We don't let the engineer specify the pump anymore. We always specify the pump.
I have a question for you.
Yeah.
How are you getting by not having to put a 100-pound pressure test on your panels?
It's not required. There's no requirement for our system.
I know in the Uniform Mechanical Code and also the IMC, they require a 100-pound test on the distribution piping, which if it's PEX tubing in the slab, then they want to see the whole thing pressurized to 100 PSI. You've not run into that as a problem?
Not at all. I think our requirements supersede that. The 100 PSI, I think, really comes from domestic use. Hydronic systems typically are never more than 30 PSI. And we test our panels to 100 PSI in our shop, but we're not going to have contractors testing them to 100 PSI. There's no need for it. If they want to pressurize the system from the manifold back to the boiler at 100 PSI, they can do that if that's running through the building or whatnot. But because our system is outside, and up to this point it has been under movable pavers, we haven't done any systems under poured concrete yet. We just haven't run into that. So our specification calls for testing to 30 PSI. We used to do it to 50, but we test them here in our shop. We do spot tests on our panels where we heat them up in an oven under pressure to a certain temperature and a certain pressure to make sure that the panels are good. And then once they are built into a row on our assembly line, we then subject them to another pressure test to 50 PSI using a very, very sensitive testing device that senses down to the thousandth of a PSI pressure drop. And so we know that if we are going to get any leakage through any of our connections and joints. And then we also do a flow test in both directions through the row of panels to make sure that no occlusions have occurred in the welding process. So that's how we test them. So that's the basic system. We usually recommend Axiom or Calefacto glycol feeders. Right now, we're shipping Axioms with a special valve on them that kicks on at 5 PSI and kicks off at 10. And the reason we like that setup is it allows us to pressurize the system to as low as, say, 15 PSI. And when the pump kicks on, the glycol feeder is going to see the low pressure behind the pump, and we don't want the glycol feeder kicking on. Now we're using high head pumps, so that's going to, if that pump kicks on full pressure, it's going to drop, up to 10 PSI on the back side, and that can kick on the glycol feeder. So we try to dial it in where we're getting those pressures as low as possible on the startup so that we can allow for the highest head pressure and flow rate on the other end going out the other side on the supply side.
Looks like a very sound mechanical plan that you've got there. The only question that I have, you've got check valves on both the supply and return lines. Is there a reason for those?
Again, that was for if this was drawn when we had a project that the mechanical room was above the installed system. And we put those in there as a suggestion if a contractor wanted to put those in so that if there was ever a failure in the system, that the entire glycol system from up above, there were spring check valves so that all the glycol up above wouldn't drain out.
Got it.
Not sure if that's even worthwhile or not.
I wouldn't.
Yeah, I think it was asking for trouble, and we're probably going to revise that and get rid of those.
A little more resistance than what's necessary.
Yeah. And this is an example of the detail we go to. This is, you can see it's obviously the Beaumont Hospital project. And because it was such an unusual layout, what we did was we color coded each loop of panels for the installers. So on their plans, when they got their plans, which you do like a, what is it? It's a super B-size sheet. And so it's something that a contractor can carry around in his tool belt. But we want it to be able to be very visible and readable and understandable of where the panels go and where the routing of the tubing goes. Like here, where my cursor is, we've got a loop. So that's showing, okay, you're going to make a loop of tubing down around underneath the pedestal to come in on number 13 here. And then from there, it's going to run back to the manifold. So we design every tube where it's going to go. We show where you're going to have to put a connector. We show how the panels connect together. Is it going to have an S-shaped tube between them? The S-shaped tube here shows how we deliver these panels. The S-shaped tube allows us to fold these rows up into three panel length rows, and they fit into a box that's 7 feet long. That 7-foot box sits vertically on a pallet, so it fits just inside of a tractor trailer with, however many boxes. I think we get 6 boxes on a pallet, and so each box is labeled all the way around it, telling you which section, zone, and row is in that box. So with these colors, you can see here there's this light blue. Well, that's down here over here. You see there's a little row up here that's light blue. Well, to get the balance right, we wanted X number of panels per row, and we wanted each row to have as close the same amount of panels as the next one going. And so that's why we'd have to combine this section with a little section up here before it returned to the manifold. Here are the yellow ones, boom, 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 back and forth before it returns. And so that's again, the kind of detail that we provide in the layout so that the contractor doesn't have to think twice about it and it's easy to install. We don't always do the color coding, but we always label them so you know which section, zone, and row is going to go where. We also provide section details so that everybody knows what's going to be required and is it really going to fit? Are we going to put the manifolds underneath the pavers on a rooftop? And is there enough room for it? Is there enough room for pipe insulation? How about putting a rim band around the perimeter so you don't have to do pedestals at the perimeter to support the pavers right at the wall? It eliminates a whole need for another pedestal that would have to be crammed in here somehow. So we think all of this stuff out. We even help design the detail of how is the railing going to connect with the pedestal mounted paver system. How is that going to be fastened? How is that all going to line up? Where are the tubes going to go? How do we get the tubes in and out of the building to the rooftop? So we work with all of those details on the projects, whatever the project demands. This is an example of how we install them. So the panels come marked with this permanently. As we manufacture the row of panels, we run it through a printer that fusion welds this label right into the plastic. This is permanent. Tells you which section, row, panel it is, and the inlet and outlet. We don't do that anymore, but we now put right there maximum 30 psi. We also put the project name and the installing contractor's name and his phone number, along with our phone number and our information up here. And that way, if there's ever a problem, somebody knows they just lift up a paver, the building manager or whatever, all he has to do is lift up the paver, see where he has to go on the manifold, turn off that row and maintain it, or who to call in an emergency. When the panels come to the project, originally the contractor to connect all the individual aluminum panels together with those push connects. So when you look at the videos on our website, that's what you're going to see. That part is eliminated now. They come in the box, you unfold them, you lay this 1x3 strapping on it, you lay it out on the ground, you unfold it, you lay the strapping along one edge, then you take those hand clamps that you can get at Home Depot. We recommend Milwaukee, they're the best. You put one on per panel, and 2 guys or more, depending on the length of the row, pick the whole row up, swing it into place, drop it onto the pedestals, and then the paver guys come in, put their pavers on there. You hook up the two ends, you're ready to do the next row. Super easy, super quick, and it's actually kind of fun to do. This is our assembly line showing where the panels have come off of the fusion welder. They're fusion welded back here at the left. We don't show that because it's proprietary, but they come out on this upper line, and then they're kicked off onto here where they're pressure tested, and then they're kicked down to here to this level where we add the foam insulation to the panels, and then down here at the end of the line they are folded up, placed into these boxes, and the boxes are all labeled around all edges, so you can, wherever you look at the box, you're going to see what's in that box. This is a CAD drawing of the panel showing how the back side is, where the insulation is CNC cut for each panel, depending on how the tube is coming out of the panel, whether it's an S tube, a straight, it could be a 90 to the left, a 90 to the right. We figured all that out. You know, contractors will always say, how did you know which way the tube was going to run back to the manifold? Well, we design it that way. We have a computer right at the head of the line where the guy welding all this together sees exactly where the tubing is going to go, and he puts the appropriate tube in the proper direction on the panel so that when it's on the job site, it all works out perfectly. The foam on pedestal mounted is notched out on the corner, so the pedestal rests right against the hard plastic, and you don't have to worry about the foam crushing on the corners. When there is full support underneath the panel, then we bring the foam all the way to the corners, and we can use between 10 psi foam, 60 psi, or 100 psi, depending on the load requirements. The full thickness of the panel is 1.4 inches thick. Other uses for our panel are geothermal. That would be the first next use that we're going to be promoting. Again, our panels are so fantastic at transferring energy per square foot that, you know, burying them in narrow trenches, 7 feet deep, provide a great alternative to slinky loop systems. They typically require you to excavate the entire yard, and then you bury the slinky loops, and then you have to refill the entire yard back up. Our system could be done in a much more efficient way, and also in shorter runs. So that's something that we're looking to get to work with some geothermal partners and getting some systems out there. So if any of you know of anybody that would be interested in that, we're looking for some partners to work with us on geothermal applications. Refrigeration is another great application. Refrigeration in stores are typically high pressure refrigeration systems out to the displays. They lose 30% of their HCFCs to the environment every year. That's very expensive and very bad for the environment. Some grocery stores are starting to go to primary, secondary loop systems where the refrigeration is held in a mechanical room and it cools a bucket of glycol or brine solution, which is then pumped out under low pressure out to the refrigeration displays. Our system would make a great system for that distribution in those displays because they're not affected by corrosion with brine solutions, and they're very efficient in transferring energy. Interior radiant heating and cooling, that's the next big application that we're going after. Our system is designed to work on that 24-inch or 600 millimeter grid module, and which is 600 millimeters typical in Europe and 24 inch in the US. That grid module is what most acoustic ceiling tile systems are done at. Our panels fit perfectly with metal ceiling, acoustic ceiling tiles. So our system is ready to go in a radiant heating and cooling system in office buildings. The big advantage there is because we're transferring so much more energy per square foot, we can run at a lower temperature or a higher temperature in a cooling scenario. The biggest problem in radiant heating and cooling, of course, is condensation on the cooling side. So we can run a much higher temperature and still be very effective at cooling compared to a tubing-based system in ceiling panels. It's a very popular system in Europe, and people are starting to consider it in the US. if you put our system in a 20-story high-rise in the U.S. with a typical replacing it with a typical HVAC system, you would add the equivalent of 4 to 5 extra stories of usable space in that building by eliminating all of the ductwork. It's enormous. And so that's a big application that we're going after. And that's why your association is going to be key in helping us, get to that market. We really want to change the way the world heats and cools all of its environments, whether it's external or internal. Trucking and shipping. What's that? You too? Yeah, absolutely.
Too.
Yeah, I mean, that's, this is a game changer. And, there's a lot of barriers to break down, but, we're already breaking them down in the snow melting arena and the pool heating arena and the patio cooling arena. And that's proving the product, and it's getting the job done where we need to get it done in a safe manner. And, the next application of these interior applications. Cooling of and heating of trucks and shipping containers, another big potential market for us, compared to HVAC in a truck, where you're blowing air through a truck and trying to distribute that evenly. We've spoken with numerous food vendors, and there's enormous food losses in shipping containers and trucking, from ice cream to fresh produce, where the temperature controls, it's a nightmare in trucking and shipping. Our system can provide very even temperature control in trucks. And then the last one would be skating rinks. Our panels, because they put out so much heat transfer per square foot very evenly, great application would be making ice for skating rinks, and we're getting together with some partners in that arena as well.
Literally, huh?
Literally. I didn't think of that. This is the end of it. Another example of some of the extremes that we do. Last fall, we were fortunate enough to finally install a system with the North American Missile Defense System at Fort Drum in Watertown, New York. The year before, they had 6 feet of snow just before they had decided to put our system in. And so they had to wait another season to get it in there. So typical of our government, they put, in particular, these pavers that are laying all over our panels to weight them down from wind lift. They put these pavers down temporarily until they get approval for our system. Ultimately, those pavers had elevator feet on the bottom of them, so they wouldn't lay against our panels. So they had to remove all of those pavers and bring in the correct kind of pavers to melt the snow around this satellite dome, radar dome that senses missiles that would be coming in over the North Pole. But it works beautifully, and it gets the job done. They needed it. This is a bomb-proof, hardened building, and they actually had a separate building for the mechanical, because you couldn't have the tubing penetrate the building. Pretty neat installation. So I thank you all for listening, and any questions anybody have at this point?
I think you've been doing a good job of answering them as they've gone along, but we'll open the floor to see if anybody has any additional questions. I have some comments for you. We're working on a project for a nonprofit in Big Sandy, Montana, and they're still trying to decide what it is that they're going to do, and we're trying to help them. They were looking at the possibility of doing radiant walls. Have you ever done anything with that?
No, but we could. Actually, I've done radiant walls with PEX tubing in shower installations, that type of thing, so that, when you sit in the shower, your back doesn't freeze. Our panels are great for that. The only concern is if somebody's going to hang a picture on that wall with a nail, how do you deal with that? And
yeah, we typically recommend they keep it below wainscot height. That way you don't, if a kid's going to put a picture up, they're usually using tape or a thumbtack and not necessarily a nail. But in a commercial setting, they would know that there was definitely water on the other side of that sheetrock, and they wouldn't be allowed to hang anything like that. And then there are actually alternative methods of being able to hang things that don't require the use of a nail. But I'd love to bring you into that project and see if maybe we can get a good demonstration site for you that we can show people that there are alternatives to radiant comfort that don't have to come just from the floor. I'm
Sure.
personally a big fan of radiant ceiling and radiant wall systems, and actually have a radiant window system at my house up in the mountains that I use to condition my house up there with.
Oh, wow. Does that particular project have a suspended ceiling where a radiant system could go in the ceiling?
It does, and he was talking about tripling the insulation that was on top of that. We could do potentially a radiant ceiling system. We haven't even done the load calculations on it yet. I've got an engineer from Patio and one of our members that's a designer that we've got involved in this project that we're just putting the drawings together now and going to do a load calculation on it and then come back in with some reverse engineering and say, well, you could do walls or you could do ceilings, or if you do the walls, you have to augment it with the ceilings, and just give them a lot of different options on what they can do. It sounds like your panel's pretty flexible in that regards.
Yeah, for a typical office building, we would say you're probably going to do between, about 30 to 40% of the surface area of the ceiling with our panels to provide the necessary heating and cooling that you're going to need. That's just a very rough rule of thumb, because our panels are putting out so much energy, or putting out or absorbing so much energy per square foot compared to a tubing system. If you use a system that like Legend is putting out, they do it in Europe where they have integrators. Armstrong Ceiling Systems has approached us where they want to integrate our panels with their tegular ceiling systems, their metal ceiling systems. Right now in Europe, they sell their panels to integrators in Europe, where they then take joist track with copper tubing and affix it to the panel, and then each panel is connected with push-on connectors to the next panel. Very awkward system. A lot of potential leak points there. And, we've designed our system from the beginning to be able to work in that kind of a scenario, where it's all fusion welded. Again, it would just be the same thing what you see here in this picture, just, upside down in a ceiling. And it should work phenomenally. We haven't done any yet because we just, one thing at a time. We've been pushing, snow melting and the pool heating.
Sure.
Applications.
Walk before you run.
Yeah, we would love to have an opportunity to do an installation like that, for sure.
Another potential application for this that crossed my mind as you were going through your slides, I don't know if you're familiar with this application or not, but it's called night sky re-radiation cooling.
And how would that be used?
Basically, you put your panels on the roof, uncovered, exposed to the night sky, and at night the outer space is minus 325 degrees Fahrenheit. So the flow of energy would be from the panel to the sky. It'll cool the panel below the ambient temperature.
Well, that would work under a patio. We actually just got specified into a project in, I believe it's in Los Angeles. It's a very high-end home, multi-million-dollar property. And the cooling loads, the engineers are having a problem with, they're using geothermal, for cooling and heating. And the cooling loads exceed the heating needs. So there's a big imbalance in the geothermal system because of that. I don't understand the details of it, but they need a way to dump the heat from the cooling at night. So originally they called us to do a 2,000-foot patio that would heat the pool and cool the patio. But now they're thinking of putting us under many, like 10,000 square feet of patios on other parts of the property for exactly what you just mentioned, for nighttime radiant cooling, to take the heat out of the geothermal system that accumulated during the day from the air conditioning loads,
right,
and dump it into the evening sky at night. And we're excited to do that.
That's a proven technology. The IKEA store here in Denver has ground source heat pump. It has vertical borehole fields that are in the floor of the basement, which is their parking garage. They have a very large truck ramp that is essentially their heat rejection method. In a cooling-dominated climate or a cooling-dominated building, the loop field has a tendency to build up a lot of residual heat to the point where there's really not a lot of room for rejection. And so they have to have another method of being able to reject it. And they're using what essentially would be a snow melt system in a driveway going into the truck loading dock to reject the excess heat out of the loop field. And the guys in the truck dock will occasionally call engineering and say, hey, it's snowing out here. You think you need to reject some heat? And they'll turn the pumps on and melt the snow for it. It wasn't meant as a snow melt system, but it works that way, obviously.
Yeah.
It's primarily just a heat rejection system to be able to send the excess heat into the sky.
Now imagine our system that's 2.5 times more effective, than the tubing system that would be used in that. How much more effective it would be at doing that. I don't know if I would want to expose our panels to direct sunlight. They are black. The resin is made black using carbon black, which is a UV protectant, but it's to a point. If somebody knew that going in, again, the panels are not inexpensive, so we'd like to see them protected, from direct sunlight as much as possible. But again, and the whole point is keeping the project aesthetic and creating a fourth dimension. And we gets back to safety, comfort, and utility, and being able to use those spaces. In places like Manhattan and Chicago, rooftop spaces are going for as much per square foot as the interior spaces on these high rises.
Wow.
And everybody is just all over putting stainless steel hot tubs on their roofs. And we even had one guy with a stainless steel hot tub with an infinity edge on a hot tub, where we were going to, heat and cool the patio and snow melt it in the winter, heat it in the cool it in the summer, and provide some of the hot tub heating with the heat from the patio as well.
Crazy.
Yeah.
Well, Robert, thank you very much for coming in here and making this presentation. I think it's a very interesting product, and look forward to you becoming a member of the RPA so that we can co-promote above and beyond this little session that we did here, and see if we can find you some homes to possibly test your product and help you prove it and bring it to the market, and see if we can get some of our members to jump on board. And the reason I asked you about Hawaii is I'm going to retire in about 2 or 3 years. And when I was there 3 years ago, one big problem that they had was that in this shoulder season of the year, the swimming pools are cold, but the deck is hot.
There you go.
And talking to the locals, they said, well, the exact opposite happens during the summer months. The pool's too hot to swim in. And so if you've got pavers with your system underneath it, it could then become a heat rejection system at night and cool the pool down so that it's comfortable for the people that want to swim in it.
Exactly.
Dibs on the Hawaiian franchise.
The job's yours.
Again, thank you very much. I appreciate it. And I would like to thank all of the people that took the time out of their lives to come and listen to the show. And as soon as I get it rendered, I will send it up to the website so that if you want to go back and refer to it later, you can see it. And Robert, I'll send you a link for your associates so that they'll have access to it too.
Thank you very much. And thank you, everybody, for listening.
You bet. Thank you, and have a good night. And we'll talk to you all in about a month.